in isomerism reactions. Not the chapter of organic chemistry. Okay, it's too long and it's too. It's not complicated. It's just too long. Okay, and only your teacher of organic chemistry who could do it. I'm just giving you some explanations, some explications, something about it, just to hear it in English, okay? So let's start about it. Okay, so isomerism is an organic compound. It's about 9 organic compounds with the same number of carbon atoms. Can we have the carbons connected in many different ways? Molecules with the same molecular formula but different connectivity or arrangements of the atoms are called isomers. Someone who couldn't speak, who couldn't understand, could cut me just to explain it in French if you want, okay? So molecules with the same molecular formula but different connectivity or arrangement of the atoms are called isomers, okay? This is taken from the Greek. Iso mean same and meros mean part. So it's the same part. It means it's the same molecular, formula molecular, the same weight, molecular weight, but it's not the same drawing in the space, not the same arrangement. Okay? So let's go behind. The third one, we have types of isomerism. Yes, we have type of isomerism, like here in the, no, the third one, not this, the third. Below, not, no, not this, below. The third one, the third one. Yes, this one. Now the third diapo. Ikram is the third diapo, not the second, not the fourth. This is the fourth or the fifth. When we have this drawing about isomerism, not this one, the other one. Now, the third one, the third, troisième diapo, le troisième, s'il vous plaît. Pas le quatrième.
Attendez, madame, donc c'est avant ce... Ah, il y a un problème de connexion parce que je suis en train de mettre le troisième et il ne s'affiche pas. C'est maintenant que j'ai remarqué.
Ah, c'est dommage. Pourquoi?
Oui, parce que j'ai mis le troisième et vous me dites le troisième, donc j'ai...
Là où il y a le schéma, là où il y a le schéma de l'isomérisation. Après, ça vient d'explication du schéma. Là où il y a le schéma.
Alors, je vais refaire le diapo. Dès le premier, vous m'arrêtez, d'accord?
D'accord, ok. Le premier, c'est le titre. Le deuxième, ce que j'ai expliqué, c'est... Voilà, ça c'est le premier. Voilà, ça c'est le deuxième. Juste après, le troisième. Voilà, le type... Voilà, c'est ça le troisième. C'est bon, vous arrêtez. Voilà, c'est ça le troisième. C'est bon. Voilà, très bien. OK. So, we've got here types of isomerism. So, the reaction of isomerism is divided on two structural or two main reactions. The first is structural isomerism, and the second is the stereoisomerism. The first one, I mean structural isomerism, is about the difference in chain isomerism, position isomerism, and functional group isomerism. And we're going to see the example, and we're going to see this in details afterwards. Okay? The second chapter, or the second part, The meaning part of structural or about isomerism reactions is stereoisomerism. So we do have geometrical isomerism and optical isomerism. This is the main parts. There is a lot of parts too, but the two ones are the most important reactions that we could found it in your second year of your study. The other one, you will go and see him in third year and in masters afterwards. Okay, so we're going to see the details. Going to the fourth, please. The fourth diapo, please. Yeah, the fourth one, yeah. So we do have the introduction of structural isomerism. So it's the compounds who have the same molecular formula but different structural formula. Okay, structure, it means the same weight, the same molecular weight, the same skeleton of the carbon, but different, some slightly different in physical properties. More branching, it means lower boiling point. This is about the chain. The position, it means that we have always the same skeleton, carbon skeleton, the same functional group, the same chemical properties, but a little bit different physical properties. Okay, and you have also functional group, which are slightly different, a different functional group, different chemical properties and different physical properties. So we're going to see this in details. The fifth one, please, the other diapo. The other one, yeah. The fifth, okay. So structural isomerism is about chain first. So it's caused by different arrangement of the carbon skeleton, as we said, similar chemical properties, different layer bits, different physical properties. And we do have, if you do have more branching, it means that we have lower boiling point. Like we said here in the example about butane. Butane here, one is in the straight chain molecule, and the other one is branched molecule, and the branched with CH3. And so these two molecules are the same. We have the same number of carbons, we have the same number of hydrogen, but their position in space, or as drawn here, are not the same. Okay, they are not the same thing. The first is straight line and the other is branched. So this little difference make two molecules different too. They make it isomer. So you do have here butane, but the other is 2-methylpropane. So this is, it's not the same, if you want, not the same molecule in the space. When we draw it, it's not the same one. They have different physical properties. They have the same chemical properties, but different physical properties, okay? So let's go to the sixth one. We have another examples. The sixth example, please. Yes. We do have here the same, as we said, the melting point here is minus 0.5 degrees, and for the 2-methylpropane is minus 11.7 degrees. It's not the same melting point. It's about physical properties are not the same. This is another example, okay? So we have chemical properties are slightly the same, physical are different, and boiling points are different too. If we have more branching, we have a lower boiling point. If you have more branching, we do have lower boiling point, okay? So let's go to the other, when you have to see position, structural isomerism about position, yeah? So about positional isomers, as we said first, we do have the same carbon skeleton. We do have also the same functional group. We have the similar chemical properties, but slightly different physical properties, okay? So here we do have the same example. We have pent 1N and pent 2N, okay? So we have to name the carbon, or count the carbons from the left to the right. From the left to the right, you have 1, 2, 3, and not right from the right to the left. The other one. So we count from the left 1, 2, 3, 4. It's very important in the organic chemistry. So we have to count the number of carbons from the left to the right. Okay? From the left to the right. So we have 1, 2, 3, etc. As we said here, we have the double bonds in the first carbon, and the second example, we have double bonds in the second carbon. So it's the same skeleton, it's the same molecular, if you want, but in isomerism, they are not the same because of their physical properties. We do have the other one, the other diapo, please, the 8th one. We have another examples of position. Positional is that what I'm going to say for halogen or haloalkane. The molecule here in green, it's about chlor. Okay, so we do have 1 chlorobutane, 2 chlorobutane. Okay, so we have to name, or they have to enumerate the number of carbon from the left to the right, 1, 2, 3, and not like we have in example, not beginning from the right. We have to begin from the left, 1, 2, 3, etc. Okay, and this is the different position of the chlor that make different molecules or different isomerism of chlorobutane. Different in their physical properties, okay, only. The other one we are going to see about functional group. The 8th, the 9th example, please. Yes. So the structural isomerism about positional. Yes, this is another example. I forgot about it. It's about dichlorobenzene. Dichlorobenzene. You have the 2 molecules of chlors, yes, in different position. I guess we've done this at the core of the course of organic chemistry. We have ortho, meta, and pa. So these 3 different manners how to draw the molecule of chlor in the benzene. Have to make it different the other from the other one. Each other is different from the other about physical properties, and they have a similar chemical properties, but different one. Okay, they are the same molecule but are different in isomerism. The 10th one, the other taboo, please. The next one, please. Yeah, this is about functional group. Okay, structure about functional groups. Of course, when you talk about alcohols, ethers, or aldehydes and ketones, or acids and esters. The position here, the molecule here in red is the oxygen. So when it's in different position in the same molecular skeleton, it's different about their behavior. I mean, chemical properties and physical properties are slightly and totally different. Only about changing the position of the main functional group. It means, oh, here, the oxygen. The oxygen is here in alcohol is at the end, but ethers is in the middle, like you see here. So this difference of position, it means we have changed the functional group, and when it changes, everything will going to change. Isomerism, property, chemical properties, and physical properties, okay? The same thing for acids and esters. Everything is going to change. The other example, please, for another examples. Yes, we do have. So, like we said, for example, for alcohols and ethers, and we do have some, we do have here their properties. The first one is methanol, it means it's alcohol, and the other one is methoxymethane, it's an ether. So we could see the difference in their properties, chemical and physical one. The next example, please. 12. Next one, please. Yes, the same example of aldehyde and ketones. The same one, the same example. Next, please. Next example, please. Always in a functional group. The same examples about carboxylic acid and esters. Yes, the next one, the fourth one. So here we have ended with structural isomers. We move there to the stereoisomerism. They are same thing like structural, but here it's different about the arrangement in space or arrangement 3D, three-dimensional space. 3D is slightly or totally different about the position and structural of the molecule. First, we have geometrical isomerism. Yes, we could move. Yes, move the next. Yes, yeah. So, like it appears here in the example. So about geometric isomerism in alkanes. I just gave an example about alkanes because please just stay. Please just stay. Yeah, just stay on. Don't move. Please come back. Yeah, please here. Come back to the 15. Yes, just stay. So I said about geometric isomerism alkanes. So we have restricted rotation of CC bound. I mean, we have here in black, it's carbon. That we have here in gray, it's hydrogen. And that we have here in green, it's about the chloride molecule. So in this position, we do have the X of O here in the double bonds, if you see, and which is in the same position, in the same side of the chloride one. We could call it Z position or cis position. And the other one, I mean, when it's the opposite of two molecules of chloride, we call it trans or E. Z and E, it's the name of, in Germany, that we said zusammen. Zusammen means together. We have together. We mean the same molecule and the same side of CC bond. And the other one is the opposite in English, but in Germany we call it Antagon. Antagon, I mean E, it means opposite side of the CC bond. We have here the axe of the carbon and the double bonds. This is the axe, and this is the reference if you want, which is in the same side, it's cis, and which is in the opposite side, it's trans. Okay, that's we call it here in isomers. The next one, please, the next diapo. Yeah, here just we explain that the isomerism in alkanes is much better, easier, and much better. We can explain it easily because when we have only one bond, like we see here, it's not impossible to do it. I mean, they don't have isomerism. Single covalent bonds can easily rotate. It's rotate on itself. It's not the case of alkenes. What appears to be different structure is not. It looks like it, but due to the way structures are written out, they are not the same.
Pardon, madam, we can't hear you clearly.
You could hear it, or would you please? Would you want to explain you in French? Or you didn't hear me? Only just to hear me.
Pas vraiment. Ça se coupe. Je sais pas si ça vient de moi, mais...
Je sais pas. Vraiment, je sais pas.
Non, on vous entend très bien.
Eh ben, ma connexion, pardon. I'm so sorry.
Il n'y a pas de problème. Je continue. I carry on, okay? You have to see to figure out about your connection. Maybe it's not me or it's not you. So we about the not the alkene, I mean the alkane of, in this case, we can do in the rotation about their axe. It means the axe of CC bond. So we could clearly here at the same molecule, because they have the free rotation if you want. But the problem in alkanes, we don't have the free rotation. We could see the next example, please. The next one, please. Yes, here. So the rotation is restricted here of CC bonds. So the groups on either end of the bond are frozen, are like rigid. They couldn't do it in one position. It's easy to flip between the two. Okay? It's easy to flip between the two. This produces two possibilities. The two structures cannot interchange easily, so the atoms in the two molecules occupy different positions in space. Okay, so we could see here in the example, we couldn't rotate the double bond is it's like frozen, it's like rigid. We couldn't rotate. It's not like the covalent or the one bond. Okay, this is the difference between alkenes and the others. We move to the next diapo, please, the 18th one. So I will come back to the cis and trans position. So should I give you some examples here about the same, in the same, the molecules in the same side and the opposite side. Okay. For much and more explanation, we have to see the law of Kahn, Ingold, and Prelog. We have to see this in your course. I don't know if this year or on the third year. I don't know. So we're going to see next time. So this is another example. Move please to the next example, please. Yeah, 19th. So isomerism in butane. We do have the 4 examples, but only to one who could consider it as geometrical isomerism. Only the two one. Okay, the other one they are isomers, only isomers, but how to choose, how to consider the two one, this one, are in geometrical isomerism. In the next one, the next diapo, I will give you some examples how to consider in isomerism like a geometrical only. Next one, the 20th one. 20th, next diapo, please. So we do have here the examples about how to tell if it exists, how to tell if geometrical isomerism exists. We do have this one, this case, and the other, the first one and the other one. The first column is about the molecules, the first molecules here on the left, and the other column is about the molecules on the right of my hand here. Okay? So in the geometrical isomerism is considered only for the first case and the last case. Okay? This is about geometrical isomerism. So we move now to the optical isomerism. Next one, please. And the last one, last meeting. So, optical molecules. No, you stay in the 20th, please. No, please, on the 20th. 20. Yes, this one. So, yes. No, not this. Not 20, 21, please. This one, chiral molecules. Yeah, this one. Thank you. Chiral molecules. When we heard about chiral molecules, it's about an optical isomerism. Chiral molecules, it's about molecules that have their image on the mirror, but cannot be superimposed. Okay, like the hand. If you put your hand just behind the mirror, you're going to see there is an image about your hand, but it's not superimposed. That means chiral molecules, and this is the optical isomerism. Okay, it's from Greek. Chiral means hand in Greek, and the analogy of optical isomerism, you have two compounds they have mirror images of each other that cannot be superimposed. Okay, superimposed. It means when you put your hand on the mirror, it's not yours. So we could have a lot of examples in the 22 chapel, please. Next one. The next, yeah. Next one, yeah. Here, you could see the two molecules. This is the mirror between them. So if you have to superimpose the molecule here in the left on one in the right, they are not superimposed. Okay, we have the black on the black, the purple on one purple, but the yellow it's not on the red. Red is not on the yellow, etc. So we have here some directions. When we put some spoons, you know that it's spoon. Spoon, when you put it behind the mirror, its image and are superimposable. Okay? We have books. You know what does it mean, books? When you put the book behind just front of the mirror, you could see that is superimposable, but there is not an image, mirror image. It's not the same thing. And likewise with the hands. They are the image of the hand, but they are non-superimposable. Okay, and so this is the case of the molecules. To be optical isomerism, you have to have the same image, but they are non-superimposable. Now we could talk about optical isomers. Please, the other chapter, please. This is 2023. Yeah, here. So in the occurrence, optical isomerism is another form of stereoisomerism. It occurs when compounds have non-superimposable mirror images. So the two different forms are known as optical isomerism or enantiomers. We have to call it enantiomers. They occur when molecules have the chiral center. A chiral center contains an asymmetric carbon atoms. It means non-symmetric, no symmetric, asymmetric, not symmetric. As asymmetric carbon have 4 different atoms or groups arranged tetrahedrally around it. We have to have 4 functional group are different the other from the other one. Like we said here in 2-chlorobutane, we have the second one of carbon, and he has 4 functional groups that are totally different. The first one is hydrogen, and the red here is the chloride, and the other one has the methyl, and the other in the right is the ethyl. So they are different, and when we put it just behind the mirror, they give us the same images, but they are non-superimposable. This is optical isomers. We move, please, to the next one. We move to the 24th slide. Okay, so stereoisomerism or chiral molecules and enantiomers are mirror images of each other, and compounds that are non-superimposable mirror images of each other we called enantiomers too. We have here another organic compound. It's about carbon. The carbon, do you know what does it mean, carbon? It's the smell of carway. Do you know what does it mean, carway? It's like Arabic, karwiya. It's the carway. And the carbon is the smell of it. It's the good smell of carway. So we move to, yes, carway is karwiya. And we could, karwiya in Arabic. Karwiya, c'est l'épice là.
Okay.
Okay, so we see about the enantiomers, and you have here diastereomers. That's the same thing of enantiomers, but are different in the position. We do have here the example in French. You could read it. I give it in French for you to explain. So diastereomers are stereoisomers that are not mirror images of each other. They are stereoisomers that are not enantiomers too. Okay, we do have the explanation of the example. It's very clear. We move to the other one, please. We move to the next slide. Sorry, the next slide, please. Yeah, we do have another example about optical isomers of aniline and methylhexane. We move to the 27th slide. So we have here, we are going to speak about the optical activity. The optical activity is very interesting and very important. When we talk about dextrorotatory or levorotatory molecules, it's about an activity optical, and we need it in a lot of fields like biochemistry and pharmaceuticals. We need this kind of optical activity in some isomers. What does it mean, the optical activity? We said we have to see here in the next slide, please. Next slide, please. We do have the next slide, the last one. So here we have here when to put the sample of an isomer in brown here. When it's written, plain polarized light enters the sample tube containing a known concentration of an optical isomer that rotates the plane of the polarized light. Yeah, the activity, the optical activity is to divide or to incline the light. When there is a light, that will be divide, or that will be in not his direction, in another direction with an angle of theta. If this theta is positive, so it's a dextrorotatory, and when it's negative, it will be levorotatory. When we said about a molecule, it's dextrorotatory. It means that she turns the light on the opposite side. It means she turns the light on the same, like we said, clockwise. Okay, it's we can rotate the plane of the light like the clockwise. And when it's a negative, it means that the compound or the isomer, he rotates the plane of light counterclockwise, and it's called levorotatory. It's really important to know about this optical activity, to use it in the pharmaceutical and biochemistry for manufacturing some drugs and some optical isomers too. Okay, so we do have some examples in the 27th slide. I write here what you need to know about this optical activity. Is common in biochemistry and pharmaceuticals. It's most amino acids exhibit optical activity. Amino acids are most important isomers to use in the pharmaceutical industry. And you do have here, of course, the meaning of they are most safer, they have low cost, etc. Okay, and we have the end. Okay, it's finished. Somebody don't understand, or do I have to re-explain it in French? Doesn't matter, just tell me about it, please. Okay, it's if okay. So I would tell you goodbye. Next time, please. Next time. Next week.
Thank you, Miss.
Thank you very much. Thank you for your assistance. Thank you for your listening. Goodbye. Have a good night. Have a good weekend too. See you or hear you, maybe hear you next week, please. Okay. Bye-bye, everybody.